Today we'll talk about doing calculus with some polar coordinates. We'll look at how to find the derivative dy dx for a polar curve and how to apply it to write tangent line equations. We'll talk about how to determine the area inside a set of polar curves, and we'll talk about how to determine the arc length of a polar curve as well. Remember these formulas, x equals r cosine theta and y equals r sine theta, that we use to rewrite between rectangular and polar forms. We'll use those when we try to find dy dx also. Excuse me. Remember, we can write r as a function of theta. So what we'll do is we'll treat these as parametric equations, where r is written as f of theta in both. And in this case, all we really need to do is use that same parametric derivative in order to write dy dx in polar coordinates. But that gets a little bit messier here, right? We know that dy dx is the same thing as dy d theta divided by dx d theta. That's using the chain rule. That's like we did with parametric functions. But the problem is dy d theta is not quite so simple. Remember, we need to find the derivative of this r sine theta function, which requires the product rule, right? So the derivative of the first times the second would give dr d theta times sine theta. That's our first term. But then we add r times the derivative of sine theta, which is cosine theta. Do the same thing on the bottom. Dx d theta becomes dr d theta times cosine, but then for the second term there, the derivative of cosine becomes negative sine theta, so we end up with a minus sign in our formula there too. You can feel free to just memorize this formula for dy dx, but if you remember where it comes from, it might be a little bit easier to remember all the parts in case you're not quite sure. Let's apply that formula to find out the slope of a tangent line. Excuse me. We've got a cardioid, r equals 1 plus sine theta, and we're looking at the place where theta equals pi over 3. So that specifies a point that we're looking at. And we want to know what is the slope in terms of x and y, as we're used to, at that particular point on this cardioid. You can sketch it to get an idea if you want, but remember, this is our formula for dy dx. This is the one we derived a second ago. In this particular problem, we've got a function of r to use, and so simply calculate dr d theta, which would be, in this case, simply cosine theta, and plug that in for these two spots for dr d theta. So we've got a cosine theta plugged in for both of those things, and we can substitute in for r the original equation, 1 plus sine theta, in those two spots. And that writes our first derivative, dy dx, all in terms of theta. A lot of times this is pretty messy, and a lot of times you can do some simplifying if you want to. I didn't bother, but you could feel free to experiment with how to simplify these fractions a little bit. Not generally necessary, though. In this case, we don't care about the slope function in terms of theta. All we want to know is the slope at a particular value of theta, specifically pi over 3. So literally just substitute in pi over 3 for every single theta into this function, and you'll get something like this, right? Once you calculate that, simplify it down, we do end up with a nice, neat, pretty -1 there for the slope. I recommend sketching out that graph or using Desmos to take a look and verifying that that does look like a slope of -1 at that place. Let's try one more where we're finding slope of a tangent line. We've got a different curve, r equals 2 cosine theta, and we've got a different angle, theta equals pi over 4. But it works basically the same way. You'll need to find dr d theta, which this time is going to be -2 sine theta instead. And that, once multiplied by sine theta, becomes -2 sine squared. Don't forget we're substituting in the original function r here, right? This one was dr d theta before. Which leaves 2 cosine squared theta being added there. Do the same thing on the bottom, plug in the first derivative there, plug in the original function there, and we get something like this. Once again, you could try to simplify this if you want to. Wouldn't bother because, again, we're just evaluating at a certain point. We're evaluating at theta equals pi over 4. So plug that in. We've got a bunch of square root 2 over 2's because sine and cosine both have that same value there. And when we simplify, we notice that the numerator comes to 0 and the denominator doesn't. So we end up with a 0 slope at that point. If you were to ask to write the equation of a tangent line, there would just be a little bit of extra work there, right? We've got a slope, you just have to go in and find out where the intercept would be. But you could do that too. More interestingly, let's talk about area underneath a polar curve. As you'd expect, a Riemann sum is what we'll want to use to estimate that area, or to precisely measure that area as we make it into an integral, right? And remember, to determine areas in rectangular, we use rectangular slices. That's not going to work here, but we'll do something similar. We'll slice these regions up that are defined from one angle to another angle. Using a sweep of an angle, we'll basically create sectors of a circle as we sweep that angle from A to B. And those sector slices instead of rectangular slices are going to give us areas that we can sum in order to approximate the sum of the polar region. And as you'd expect, since we're using circles and not rectangles, the integral will look a little different. Remember, there's a star here because we're looking at some angle within each slice. We can evaluate that value. We can plug it into our function. We can square it and multiply by 1/2. That's, remember, the formula for the area of a sector. And then when we sum up a bunch of those sector areas, we'll end up with the total area. Again, to make this into an integral, we let n approach infinity, so we generate a definite integral from a to b. Remember, everything's in terms of theta here, so a and b represent those starting and ending angles. And our integral is just 1/2 of our f of theta function squared. Let's try one. So we've got the curve r equals cosine 2 theta, and we want to know what is the area enclosed by one single loop. As a reminder, that is a rose with 2 times 2 equals 4 petals. Since it's a cosine-based rose, we know that one of the petals does max out along that angle of 0. If we want to know the area inside one petal, we'll just need to choose an angle that begins a petal and choose an angle that ends that same petal. Here they chose negative pi over 4 to pi over 4. You could try other angles too. We know that both of those will work because if we substitute in negative or positive pi over 4 for theta, we're evaluating cosine of twice that angle, so cosine of pi over 2 or negative pi over 2, both of those become 0. So those are points where the graph crosses the origin or the pole. So we can use those two, but you could also start at pi over 4 and go to 3 pi over 4 if you wanted, or between 3 and 5 pi over 4. You'll get the same area. You'll get just the area of one of those petals, those leaves. So let's take a look, right? If we use the given bounds that they suggested, negative to positive pi over 4 for our integral, we're integrating 1/2 r squared d theta. Remember, r represents the radius. That's our function cosine 2 theta. So our integral, written completely in terms of theta, looks like this one. 1/2 can be taken out of the integral. With the same bounds, we have cosine squared of 2 theta. Now, this is where we might want to brush up on those integration techniques with trig functions in them. This is a cosine squared. We can use essentially a power reduction or a cosine squared formula to rewrite that. That's like 1/2 times 1 plus cosine of 4 theta. Doing that is important because now we've removed the squared piece from the cosine function, so we can pretty easily distribute this 1/2 or factor it out and integrate both of those two terms separately. Right here I factored out the 1/2 to leave a 1/4 coefficient, and then integrate each piece. Integral of 1 becomes theta. The integral of cosine 4 theta becomes sine 4 theta with another factor of 1/4 in there because of the chain rule. And then we evaluate that definite integral at the two bounds. Plugging in the upper bound and lower bound and subtracting, multiplying by that 1/4, leaves a final amount, and you should verify that, of pi over 8. That represents the area of one single loop of that curve. Let's try another one. We've got, this time, 2 different curves. We want to know the area that is inside of the region 3 sine theta, which is a circle. And we want to know the area that is not only inside that curve, but outside the curve, the cardioid shape 1 plus sine theta. So again, you should practice sketching those, getting familiar with what those graphs look like, at least a little bit. But this is what we've got. We know that there's a crescent shape that we're trying to determine the area of, between those two angles. Now, one question is, how do you find those angles of intersection? And I didn't write it out in these notes as easily as you could see it here. But the goal would be to solve those trig equations. So literally solve these two as a system of equations. You can set one equal to the other, so 1 plus sine theta equals, sorry for the bad handwriting here, equals 3 sine theta. If we set those equal to each other and solve, then we can determine all the different angles where where those two curves are going to intersect. In this case, the two consecutive solutions would be pi over 6 and 5 pi over 6. And so that we use those as the bounds of our integral. Since we're looking for the difference between two curves, we need to subtract them. So we'll write two integrals, one for the outer function, which is the 3 sine theta function, and one for the inner function, which was the 1 plus sine theta function. Set up both using the 1/2 r squared formula with the same bounds for both, pi 6 to 5 pi over 6. And then we do some calculus to compute that area. Here we can actually, and this is a little bit strange, you don't have to do this, but what I did is sort of cut that distance in half, right? Instead of going up to 5 pi over 6, I changed the upper bound of those integrals to pi over 2, which means that's only the first half of that shape, and then I doubled it to compensate for that. You can certainly do that. You don't have to, though. You're completely fine to leave those bounds the same. Either way, simplifying our integrands a little bit, we get 9 sine squared for the first one. And for the second one, we'll end up with, you'll need to FOIL this piece out actually, right? We'd have 1 plus 2 sine theta plus sine theta squared. We can actually combine those integrals together since they're written with the same bounds. And so I did that to combine those two sine squared terms next. Right, so we end up with 9 minus 1. Don't forget to distribute this negative here. So we end up with 8 sine squared theta minus 1 minus 2 sine theta inside the same integral here. And then from there we can integrate term by term. You'll end up with something that looks like this, right? We reach 3 minus 4 cosine 2 theta minus sine theta. Excuse me, which actually once we integrate that, this is actually using a little bit of a trig identity here. You can rewrite 8 sine squared theta into this form, which helps a little bit with the integration. So then that way we've got an integral of 3 theta for the first term, using the chain rule a bit, negative 2 sine 2 theta, and then positive 2 cosine theta. And when we evaluated those definite integral bounds, we reach pi. Let's take a look at one more idea dealing with polar calculus, and that's arc length. So remember, we talked about those parametric derivatives, dx d theta as dr d theta cosine theta minus r sine theta, and similar for dy d theta. If we want to know the sum of the squares of those two things, this is thinking about sort of a right triangle, right? We're creating this hypotenuse that way. Algebraically, that looks something like this. It looks like dr d theta squared cosine squared theta. Again, we're just foiling this out. Minus 2r dr d theta times cosine times sine plus r squared sine squared theta. Plus this other stuff, right? Dr d theta squared times sine squared theta plus 2r times dr d theta sine theta cosine theta plus r squared cosine squared theta. This actually simplifies pretty nicely. We're kind of just deriving a formula here. You're not going to have to do this, this kind of complicated setup here. But all we need to do then is simplify that to dr d theta squared plus r squared using that Pythagorean identity again. We've got the sine squared and the cosine squared that we can deal with. And so what that boils down to is this arc length formula, right? We end up with the integral from a to b, using the starting and ending angles for our arc, of the square root of r squared plus dr d theta squared, d theta. You can just memorize this and use it. You don't need to know how to derive it. But that's how we'll calculate the arc length for a polar curve. We'll try one example of that too. So suppose we've got that entire curve r equals 1 plus sine theta. We can measure the length of that curve using that integral formula, using the arc length. Again, this is a cardioid that goes all the way around, so we'll integrate around the entire unit circle from 0 to 2 pi. And in order to calculate the whole length of the curve. We'll use our formula r squared plus dr d theta squared. And for each of those pieces, we're going to plug in, like we did for the derivatives, right? We'll plug in 1 plus sine theta for r, and we'll calculate dr d theta to plug in there for the second piece. So we plug in 1 plus sine theta for r. We find the derivative, which is again just cosine theta, and we square it for the other term. And this integral becomes our solution, right? We integrate, we can simplify this a little bit, to 2 plus 2 sine theta. I would use technology for this one. Don't worry too much. This one actually comes out to a nice exact value of 8.